So this is telling us about an application of this. The rate of fluid flow within a vessel can be measured using the induced EMF when the fluid contains charged ions. A small magnet and sensitive voltmeter calibrated to measure speed are used. This can be applied to measure the flow of blood which contains iron in solution in the human body. If the diameter of a particular artery is 2 millimeters, the strength of the magnetic field is 0.1 Tesla, and the measured EMF is 0.1 millivolts, what is the speed of the flow of blood within the artery? So we are just taking these numbers that we know, we're applying a magnetic field that we know, we are getting a voltage that we know, and from this we can calculate the speed that blood is passing through this artery. So here is our diagram. So first of all, let's write down what we know. So our diameter of the artery is 2 millimeters. There. That is 2 millimeters. We have a magnetic field of 0.1 Tesla. And we have an EMF generated of 0.1 millivolts. Okay, so from our equation previously, epsilon LVB, what are we looking for? We want V. So if we rearrange this, V is going to be equal to epsilon divided by LB. All right. So what's epsilon?
0.1.
0.1? This is millivolts. You need to divide it by 1,000. So 0.1 times 10 to the negative 3. Okay. B is easy. B is 0.1. Now this is where this equation or this example is a little more difficult. The length of our conductor is a little bit hard to understand. So I'm going to draw a different diagram for you. This is a cross-section of the artery. Okay? This is a cross-section of the artery, and we're just doing it like that. All right? So this cross-section here is just looking straight down here. Now, as the blood flows through the artery, the blood itself can be considered a conductor because the iron is passing through it. There's obviously lots and lots of iron ions within the blood. Our length is actually this cross-sectional length. Because as blood is flowing like this, anywhere, you know, you can sort of put a probe down and measure the ions going through it. So it's just the diameter of the artery. Okay? It is just, yeah, there's blood flowing out of here the whole time, but it's that length that we're interested in. That is the length of the conductor that is moving through this magnetic field. To put it another way, if this is the blood moving out of the artery, this is the length of the conductor because that's the direction it's going at. You can think of it as a very, very long, or sorry, very deep conductor, I guess, but not a very long one. Okay, so as it goes through, that is your conductor length. Okay, so our conductor length is 2 millimeters, so just 2 times 10 to the negative 3 meters times 0.1. So our speed then, 0.1, 0.05? It's 2 times 0.002. 0.5. All right, hang on. Not that I don't trust you guys, but I'm not paid to trust you. 2 times 10 to the negative 3. Times 0.1, and I get 0.5. Yep. 0.5 meters per second. So the hardest thing about this problem is working out what the length of the conductor is. But this is just a very, very short conductor moving with a very, very sort of deep conductor.